Okay, if I may have your attention again, it's time for next talk by Matthias Larsen, this time about his unikernel and how he can run MPI code faster. Stage is yours.
So, hello everyone. You can hear me well? Okay, I hope it's okay. Thank you. Yeah, I'm Matthias Vada. In this presentation, I'm going to talk about deploying MPI applications using Toro unikernel. And this is an exploratory work. So, it's an area that I am still investigating. So, at the end of the presentation, feel free to ask me any question because I'm still benchmarking things. I'm not pretty sure where I'm going. So first, I would like to present myself. I'm passionate about operating system development and mutualization, and I have been working in these companies. This is my email and my GitHub profile if you want to get in touch or if you want to see some of my projects. This current project is not related with my current work, so it's something that I'm just doing when I have some free time. I would like to start, but what is my intuition about what is an MPI application? I am not an expert on MPI, so it is what I understood since 2 years I have been working on this. So it is an application that compiles with an implementation of the MPI standard. So there exists several implementations of the MPI standard. The standard defines a set of APIs to synchronize and communicate parallel instance of the MPI application. So for example, we have this sort of API like MPI barrier, broadcast, and all reuse, for example, just to set some of them. My impression is that the only performance matter when we deploy MPI applications. So I have the feeling that the virtualization is not very popular in HPC, or that's at least my impression, for the overhead that this adds. So my thought were that maybe MPI applications may benefit from the unikernels because, for example, syscalls are expensive, so in unikernels we remove that. We have calls, threads are cheaper than process, so you may know that we are not switching the page directory every time we are doing context switching in a unikernel. Depending on your application, you can completely remove the scheduler because you are going maybe to run only one thread per core or something like this. You can rely on communication on shared memory, for example, in the case of unikernels. And sometimes, this is something that I just added, sometimes perform better than a general operating system as a guess. And I say this because sometimes you can configure, you can tweak your operating system to reach good performance, let's say. So yeah, well, this is the diagram or the components that they are involved when you are deploying an MPI application using a general purpose operating system. In this case, I'm thinking that the MPI application is running as a virtual machine, but the diagram is more or less the same in case as it is bare metal, right? So what we have is your MPI application, then it compiles with implementation of the MPI standard, for example, OpenMPI, and the OpenMPI is going to use some syscall to communicate with the operating system to get some service like, scheduling, file system, networking, and so on. So what unikernels propose is, well, let's take that about the scheduler. So the scheduler in Toro is quite simple, and also, well, here is not a scheduler, it's the way that Toro creates threads. You have a dedicated API called a begin thread, but it's a parameter that has to tell where the instance is going to run. So you have to set up where the core, where you want that function to run. Otherwise, it's going to choose all the times the booting core. The scheduler is quite simple. It is a cooperative scheduler. So, the thread is going to do something and then call systhread switch, which is going to invoke the scheduler. And each scheduler, I think I present that in the next one. But each scheduler is independent one another. So there is no communication between the instance. So each core is scheduled completely independent one another. And the algorithm is quite simple. It's going just to choose the next thread that is ready, not more than that. And the idea behind that is that the idea was to have instances of the kernel that don't require any mechanism to synchronize the instance. So there is no spin lock or something like this. So all the access to the kernel data is lock-free. So I just talked about the scheduler. Now I'm going to talk about the memory. Also in Toro, memory is dedicated. So when the kernel initializes, is split the memory in regions, and then all the allocations happen from that region, depending the core. So the splitting is quite simple. It's just split by the number of cores. So if you have 2 cores, you're going to split in 2 the whole physical memory. And if you have 3, it's going to split in 3, and so on. So for a moment, this algorithm is quite simple, and maybe it could be improved for sure. So for example, we have a memory allocator that since each region is assigned to different core, the way that we implement the allocator doesn't require any synchronization between the core. Keep also the same idea that each instance runs independent one another. So for example, when a thread has to allocate memory, it's going always coming from the same region. And also doesn't require any synchronization between the cores and so on. The idea behind this was also to try to leverage from technologies that Intel could pass. You can have a non-uniform memory, and then you have faster access to some regions. And in a general way, all the kernel data in Toro is per CPU variables. So it means that doesn't require any synchronization between the core to access kernel data, let's say. And also to access faster to these per CPU variables was using the CS register, for example. And this is an improvement that I did, I think, a couple of months ago. So we have a table and it's faster accessed through the CS register, which is pointing to that table. I don't remember exactly the mechanism, but it is. I think I have a blog that I wrote about that. Yeah. And all the access is lock-free. The only moment that we require synchronization between the cores is when we wanted to, for example, create a thread from one core to another. We need to synchronize somehow the cores to migrate one thread to another, something like this. But it's the only moment that we need it. Otherwise, this is completely independent, all the instance. To end the principles of Toro, we're going to talk a bit about the core-to-core communication. And the idea was to, even if you, as a user, you can implement anything on shared memory as you want. I decided to implement virt.io over shared memory. So each core has a set of vir queues that allows to get data from a remote core and send data to another core. And it was just a bit of, to have fun to do it like this. And try to see if I can implement virt.io like this. And the idea is that the communication is core to core. So you don't have only one queue per core. You have as many vir queues as you need to communicate one-to-one for each core. I don't know how to say it exactly, but this makes that you don't require any any protection to send or keep the exclusive access to these peer queues, because you have only one consumer or one producer and so on. And relying on this mechanism, then I could implement the APIs from MPI, like MPI gather, broadcast, and MPI scatter, which are functions that require communication between the core. So from the root core or to the root core and so on. So I think I will just talk a bit about the benchmark I have been done. Feel free to comment about this because I'm not really sure about the numbers I'm getting. What I did was to choose a set of well-known benchmarks called OSU Micro-Benchmark, which is, since that it is used for benchmarking different implementations of the MPI standard, and I pick up two of them, the OSU barrier and the OSU all reduce, which what they do is just stress some function. So for example, the OSU barrier stress the MPI barrier function, which is something to synchronize the instance of an MPI application. It's just a software barrier, let's say. And the other one, the all reduce, is stress the MPI all reduce function, which is going to send some vector to the root core, process something, and get back the result to the other cores or other instance. What I did was comparing with Linux bare metal and Linux in a VM, and I used I pick up this machine from Equinix, which is an ABD Epic with 24 cores and 64 GB. And the host I use it for the VM is Ubuntu with isolated cores. No, sorry. Yeah, with isolated cores. And I run I used KVM QEMU as hypervisor. And sorry, no, the host was Ubuntu and the guest was Fedora 38. What I did is, in this particular case, what I did was to use a huge VM with 16 cores. Maybe it's not the most common case for MPI. People have several nodes instead of putting everything on the same. In my case, I was trying to play with this, so I decided to use a huge VM, let's say, and then compare it with Toro, right? So this is how I launched the benchmark. So for example, I am using 16 threads, for example. I don't exactly. Since I'm not an expert in MPI, I'm not really sure if this. I mean, if the MPI RAM, for example, is really using one core per thread, it will not be optimal otherwise, I think. And I was launching for 1,000 interaction. So this is the result for the Linux bare metal. No, Linux in a VM, sorry. Yeah. So these are the numbers for the OSU barrier, which is this test. So you can see that there is a quite huge difference between the Linux VM and the unikernel. But still, I have to redo these numbers. I'm not really sure about that. I mean, because they are one order of magnitude, at least. At the beginning, I was interested to compare with Linux bare metal, because I think we can achieve something like this in a VM. But then when I started to play with Linux VM, I say, well, there's a huge already difference with the VM. And also, I was comparing with also already used, as I said before, in particular with that side of vector, and also there's quite huge difference with Toro unikernel. So in the two cases are 16 cores in the VM and a Toro unikernel too. I think that's all about the benchmark. To have this number also, I figured out that some issues. In particular, I don't know if you were measuring something in VMs. In particular, in KVM, the RDTCC register is not emulated, so you have to be careful when you use that. And for example, you have to, when you are doing numbers, you have to check that the KVM is still in time. So if you make the difference, it's not going to work always. So you have to be careful about that. Yeah, that's all I think. Yeah.
Thank you. We have some time for questions. Please go ahead. The mic is dying, so Matthias will not repeat it.
So MPI is usually used over the network, right? Isn't it a huge limitation that you're only doing local communication?
The question, well, it's not a question, I think it's just a statement, right? It's a question?
Yeah.
Okay. Yeah, it's a pity I'm not doing, your question was why I'm not doing communication between the VMs using this implementation?
Yeah, basically this implementation can only run on a single node, but people are routinely using MPI on clusters with tens or hundreds or thousands of nodes, right?
Yeah.
So,
why?
yeah, do you have any plans to extend that?
Well, I'm thinking about that, yeah, because not the first time that they mentioned this, and maybe create some interface, I mean, use, I don't know, Virtual.net or VSOC to communicate with other instances, so you will have multiple VMs running that. But, yeah, for the moment, yeah, maybe I will do it soon. I'm not really worried about that, yeah. Oh.
More questions? Okay,
Which MPI implementation are you implementing in your solution? Because there are different kind of version of the MPI or pitch or so on. Which one are you based on?
I'm not really sure, because what I'm doing is just trying to read the semantics of MPI and trying to implement it at code. And the number of the function I implemented is based what is the benchmark. And that's all. This is what I'm doing. No more than that.
We have a tool, a library, which is writing MPI codes. It's called Weave MPI.
Okay.
There was a call just before on the HTC room.
Okay.
So maybe you can see that on the video and get that for
Cool.
your information for different
Okay, cool.
people that calls.
Thank you.
yes.
Do you have numbers on how it's scaled when you increase the number of cores compared to the implementation of the
Do you mean if I have numbers regarding when you increment the number of nodes, how that behave? Yeah.
not to just increase the number of cores and see
I'm still doing that numbers. Yeah, but the difference is still there. I mean, between the VM and the Linux implementation with the Toro, still a difference in the sense that it's faster, let's say. But I'm still doing those numbers too.
there is no point where the line is processed.
I don't know.
Do you have a hunch about the big performance difference between an HVM and an
The question is if I understand why we have that difference. I don't know. I'm trying. I mean, there are a lot of ways to tweak Linux to make it more performance. Maybe that I'm lacking that. And if you tweak it, you're going to just dramatically drop that difference, and at the end it's only configuration. But I'm not really sure from where it's coming. But I said before, it's still numbers that I'm working on.
Okay, I think we are running out of time, so Matthias, thanks again for the talk.
Cool. Thank you.
We have a short break of 5 minutes, and after that we will have talk back to back without any break.